Look out into the night sky past the shimmering veil of our atmosphere. You see points of light, distant suns, entire islands of stars. You see the Milky Way, a luminous river splashed across the darkness. Everything you perceive, every star, planet, nebula, and galaxy, is part of a grand visible cosmic tapestry. But it is a lie, a beautiful, intricate, and profound deception. Because everything we have ever seen, everything humanity has ever charted, is barely 5% of what is actually out there. The rest, the overwhelming majority of our universe, is missing. It is a substance that does not shine, reflect, or cast a shadow. An immense invisible ocean in which our galaxies are but glowing plankton. It is a cosmic phantom. Its gravitational embrace, the only reason our starry homes don't tear themselves apart. We have given this enigma a name that reflects our own ignorance: dark matter. For nearly a century we have hunted for this ethereal ghost. We have built colossal detectors deep underground, in abandoned mines shielded from the constant chatter of the cosmos. We have waited in perfect silence, listening for a single fleeting whisper from the unseen world. But the ghost has remained silent, its nature an infuriating mystery. Until now. From a laboratory in Japan, a new sound is beginning to emerge. Not a shout, but the faintest of murmurs, detected not by a giant trap, but by a device of almost unimaginable sensitivity. A breakthrough from Tohoku University is promising to pull back the curtain to make the invisible visible. This is the story of a quantum key, poised to unlock the greatest secret of the cosmos. And in doing so, it threatens to change everything we thought we knew about reality. Our quest to understand this unseen substance began not in a sterile lab, but in the keen eye of a brilliant and notoriously difficult astronomer. In the early 1930s, the Swiss scientist Fritz Zwicky turned his telescope towards the Coma cluster, a staggering congregation of galaxies. He observed their frantic, chaotic dance, measuring their velocities. What he calculated sent a shockwave through his understanding of physics. The galaxies were moving with such astonishing speed that the visible matter within the cluster, all the stars and gas he could see, could not possibly hold them together. The gravitational glue was simply not strong enough. By all rights, this magnificent celestial city should have flown apart eons ago. Zwicky, a mind unbound by convention, proposed a radical idea. There must be something else there, something he couldn't see. A tremendous amount of hidden mass, a form of Dunkel materia or dark matter, pervading the cluster and providing the extra gravity. His calculations suggested this invisible material outweighed the visible matter by a factor of hundreds. It was a staggering claim, and for decades it was largely ignored, dismissed as the fanciful thinking of an eccentric mind. The idea of a universe dominated by an invisible component languished in obscurity. It would take another 40 years and the meticulous work of another visionary astronomer for the ghost to reappear in our data. Her name was Vera Rubin. In the 1970 seconds, she wasn't looking at clusters of galaxies, but at single ones. She undertook the painstaking task of measuring the rotation of spiral galaxies, expecting to find something straightforward. Physics dictated that stars near the galactic edge, far from the dense, bright center, should move more slowly, like the outer planets in our solar system. But that is not what she found. In galaxy after galaxy, her data revealed an impossible truth. The stars on the outer fringes were moving just as fast as those near the core. This flat rotation curve made no sense. It was like watching a spinning merry-go-round where the horses on the outer edge kept pace with those in the middle. The only way to explain this baffling observation was to resurrect Zwicky's ghost. There had to be a massive, invisible halo of matter surrounding each galaxy, its gravitational influence extending far beyond the visible light. Vera Rubin's work was undeniable, her methods impeccable. She had provided the first robust, compelling evidence that our universe was not what it seemed. The luminous structures we cherished as the building blocks of the cosmos were merely the decorative lights on a vast, unseen scaffolding. The era of the dark matter hunt had officially begun, and with it came a profound and humbling realization: we were strangers in our own universe. So what is this ethereal substance? For decades, the leading hypothesis centered on a class of particles predicted by our theories but never seen. They were called WIMPs, or weakly interacting massive particles. The name itself paints a picture. These were imagined as heavy, slow-moving particles, like subatomic cannonballs, that only interact with normal matter through the weak nuclear force and gravity. This meant they would stream through the Earth, through our bodies, through everything, almost completely without effect. To picture the challenge of finding a WIMP, imagine you are blindfolded and standing in a colossal silent stadium. Once every hour, someone somewhere in that vast space throws a single tiny grain of sand at you. Your only hope of detecting it is if it happens to make a direct, perfect impact on a microphone you are holding. This is the principle behind the great WIMP detectors. Deep underground, vast tanks of purified liquid xenon or germanium crystals wait in shielded silence. Scientists reason that out of the trillions of WIMPs passing through the Earth every second, one might strike the nucleus of an atom in the detector. This collision would produce a minuscule flash of light, a tiny vibration. It would be the ping of the grain of sand hitting the microphone. For years, these monumental experiments have listened. From the Gran Sasso National Laboratory beneath the Italian Alps to the Sanford Underground Research Facility in a former South Dakota gold mine, humanity has built silent sanctuaries holding its breath, waiting for a signal from the dark. But the silence has been deafening. No definitive reproducible WIMP signal has ever been found. The lack of discovery has led to a slow, creeping crisis in cosmology. Perhaps we have been searching for the wrong thing entirely. What if dark matter is not a heavy, rare cannonball? What if it is something far stranger, far more subtle? What if it isn't a particle in the traditional sense at all, but a wave? A pervasive ultralight field that fills all of space. This is where a new candidate emerges from the theoretical shadows, the axion. The axion is a hypothetical particle originally proposed in the 1970 seconds to solve a completely different problem in particle physics. But its properties make it an exquisite candidate for the cosmic phantom. It would be extraordinarily light, billions of times less massive than an electron, and it would barely interact with normal matter at all. If WIMPs are like cannonballs, axions are like a whisper. If the universe is an ocean, WIMPs are like a few scattered heavy stones at the bottom. Axions, in this analogy, are the gentle, rhythmic, and ubiquitous tide itself. You don't catch a tide with a net. You don't detect a whisper with a microphone designed to hear a gunshot. To find the axion, you need a new kind of instrument. You need a device that can feel the most subtle vibration in the fabric of reality. You need a quantum sensor. This is the frontier where the team at Tohoku University in Japan has made its mark. They have stepped away from the grand brute force approach of the WIMP hunters and have instead embraced the delicate, almost mystical world of the quantum realm. To understand their breakthrough, we must first appreciate the bizarre nature of the world they are harnessing. Quantum mechanics tells us that on the smallest scales, reality is a shimmering, uncertain place of probabilities. Particles can be in multiple places at once in a state called superposition. They can be linked across vast distances, a phenomenon known as entanglement. This quantum world is incredibly fragile. The slightest disturbance from the outside world, a stray photon, a tiny vibration, a change in a magnetic field can shatter this delicate state, forcing it to choose a single classical reality. For most of computing and engineering, this fragility is a nuisance to be overcome. But for the scientists at Tohoku, this exquisite sensitivity is the entire point. They have turned a bug into a feature of cosmic significance. Their goal was to build a system so perfectly isolated, so exquisitely balanced, that it could be perturbed by the faintest possible influence, the gentle passing wave of a hypothetical axion. Imagine a luthier crafting the most perfect musical instrument ever conceived. It is not a drum or a trumpet, but a wind chime of impossible delicacy. It is constructed from a single flawless crystal, its internal structure forming a lattice of atoms vibrating in perfect unison. This instrument is housed in the most silent room ever built, a chamber shielded from all outside sound, light, and vibration. It is cooled to temperatures colder than deep space, just a fraction of a degree above the absolute zero of temperature, where all atomic motion nearly ceases. In this state of profound cold and silence, the crystal wind chime enters a quantum state. Its atoms are not just still, they are in a collective, coherent superposition. They are a single quantum entity, humming with a precise resonant frequency. This is the heart of the Tohoku device. It is a quantum system held in a state of suspended animation, waiting, listening, feeling. Now imagine the ghost of the universe, the axion field, as a constant, unfathomably gentle breeze flowing through this silent room. To any normal instrument, this breeze is undetectable. It passes through the walls, through the equipment, as if they weren't there. But our quantum wind chime is different. It is tuned so perfectly that if this ethereal breeze has the right frequency, it will cause the chime to resonate. The collective quantum state of the atoms will begin to oscillate, to vibrate in a new distinct pattern. It would be a hum where there should be absolute silence, a rhythm emerging from the quantum void. This is the signal. This is the sound of dark matter. The technical name for their apparatus is a cavity haloscope, but this clinical term belies the sheer artistry of its construction. They employ powerful magnetic fields to act as a catalyst, theoretically encouraging the axion to convert into a detectable photon inside a resonant microwave cavity. The true innovation, however, lies in how they listen for this photon. They use devices called Josephson parametric amplifiers. These are the pinnacle of quantum electronics, capable of detecting energies so minuscule they approach the fundamental limits set by the laws of physics itself. It is the act of listening for a single quantum of light, a single particle of energy generated by the whisper of the cosmos. The engineering challenge is monumental. The team must distinguish a potential axion signal from the inherent quantum noise of the universe, the constant fizz of virtual particles popping in and out of existence. It is a search for a single pure note in a hurricane of static. For years, the researchers at Tohoku, led by a team of dedicated physicists, have been refining their instrument. They have battled cryogenic leaks, electromagnetic interference, and the maddening persistent quantum noise that threatens to drown out any real signal. Their laboratory is a cathedral of modern science, a labyrinth of stainless steel superconducting magnets and delicate wiring, all dedicated to creating a tiny pocket of the universe, more silent and more stable than anywhere else in nature. Each calibration, each cooling cycle, each data run is an act of profound patience and faith. Faith in the theories that predict the axion, and faith in their own ability to build an instrument sensitive enough to hear its song. And then one day, amidst the endless stream of random data, a pattern begins to emerge. It isn't a dramatic eureka moment, a sudden loud discovery. It is far more subtle, appearing first as a statistical anomaly, a slight bump in a graph where there should be a flat line, a tiny persistent excess of power at one specific frequency. At first, it is dismissed as a system artifact, a glitch in the electronics, a new source of terrestrial interference. The team works relentlessly to eliminate every other possibility. They reshield the experiment. They recalibrate the amplifiers. They check and recheck their code, their calculations, their hardware. They try to make the signal go away, but it remains. As they accumulate more data day after day, week after week, the statistical significance grows. The bump in the graph sharpens its profile, becoming clearer. It is a narrow, coherent peak, exactly what one would expect from a population of cold, slow-moving axions that form the dark matter halo of our own Milky Way galaxy. The atmosphere in the control room shifts from skepticism to a tense electric excitement. Could this be it? After a century of searching, after decades of frustrating dead ends, is this faint, persistent hum the voice of the unseen universe? The confirmation process is painstaking and mercilessly rigorous. They must prove to themselves and then to the world that they have not been fooled. But the evidence mounts, each new test reinforcing the last. The signal is real. The moment the discovery is announced, it will not merely be a headline, it will be a seismic shift in the foundations of human knowledge. Everything changes. The first and most immediate impact will be on our map of the cosmos. For all of history, we have been cosmic cartographers drawing a map of a continent while seeing only its streetlights. With a confirmed detection of the axion, we will finally have a way to see the continent itself. New telescopes, new detectors based on the Tohoku principle will be designed. They won't look for light, but for this faint quantum resonance. We will be able to map the vast invisible structures of the universe. We will see the great filaments of dark matter that stretch between galaxy clusters, the cosmic web that serves as the blueprint for all creation. We will be able to watch how galaxies form and evolve within their dark matter halos, testing our cosmological models with breathtaking precision. It would be like giving sight to the blind. Our picture of the universe will become immeasurably richer and more complete. Beyond cosmology, the discovery of the axion would shatter the bedrock of particle physics, the standard model. This elegant theory describes all the known particles and forces, and it has been spectacularly successful. But it has no place for the axion, no explanation for dark matter. Finding the axion would be the first definitive piece of evidence for physics beyond the standard model. It would be a signpost, a clue pointing the way toward a deeper, more fundamental theory of everything. Physicists would finally have a tangible experimental thread to pull on, one that could unravel the mysteries of supersymmetry, string theory, or other exotic ideas currently confined to blackboards and equations. It would ignite a new golden age of physics, a rush of theoretical and experimental work not seen since the early 20th century. And then there is the future, the distant speculative horizon. Whenever humanity discovers a new fundamental aspect of nature, we eventually learn to harness it. We discovered the electromagnetic field, and it gave us radio computers and light. We unlocked the secrets of the atom, and it gave us nuclear power. What might we one day do with a pervasive, nearly non-interacting cosmic field? The possibilities are the stuff of science fiction, but they are not impossible. Could a deep understanding of the axion field lead to new forms of communication that could pass through planets unimpeded? Could there be a way to manipulate this field to extract energy from the most abundant substance in the universe? Could it be a key to understanding even deeper mysteries like the nature of dark energy or the origin of the Big Bang itself? These questions are for our children and our children's children. But the journey to answering them will begin with this first faint signal from a quantum sensor in a quiet laboratory. The breakthrough at Tohoku University is more than just a scientific achievement. It represents a philosophical turning point for our species. We are creatures of light. Our senses, our biology, our very consciousness evolved to perceive a tiny sliver of the electromagnetic spectrum. We have built our reality around this limitation. The discovery of dark matter, the confirmation that we are adrift in an immense invisible reality, is a profound lesson in humility. It tells us that the universe is not designed for us, that our senses are not a reliable guide to the true nature of what is. We have been living in a beautifully lit room, unaware that the house itself, the city, the entire world outside, is constructed from something we could never perceive directly. To finally detect the substance of this hidden world is to step out of that room. It is to acknowledge that our experience is not the totality of existence. This quantum sensor is not just a piece of technology. It is a new sense organ for humanity, an extension of our minds, allowing us to touch the intangible, to hear the inaudible. It connects us to the 95% of the cosmos that has been until now utterly alien to our experience. The cosmic phantom is no longer a ghost in the machine. It is a fundamental part of the machine itself, a part we are only now learning to recognize. The faint hum detected in the deep cold of the Tohoku experiment is the beginning of a new conversation, a conversation between our luminous, familiar world and the vast, dark and mysterious universe that has silently cradled us all along. We are on the cusp of understanding not just what the universe is made of, but our true place within it. The journey has been long, from a wild idea in the mind of Fritz Zwicky to an undeniable signal in a quantum device. And now, for the first time, we are truly beginning to see in the dark.